chapter 15, which is entitled regression models in general, but we're going to focus on one particular type of quadratic model. And if you recall, the basic assumption of chapter 13, and likewise up until now in chapter 14, is that the data follow the straight line. That if you graph the x and the y, that the underlying model, the underlying data, will more or less follow a straight line. The problem is, what if your data follows a curve, like these examples from the slide? It seems to be a curve. This shows you the residuals. We haven't really talked too much about residuals in these videos so far, but the top two panels indicate there's a curve to the data. How do you deal with it? Well, if the curve, very often, most curves can be a lot of curves can be approximated by an exponential function, and there's ways of dealing with that. But very often the curve can be approximated by a quadratic function or a parabola, or part of a parabola. This looks like part of a parabola, and so in order to understand how you would deal with that data, we have to remind you of the mathematics of a parabola. I'm going to, at this point, turn to the right side of the board and remind you, just like y equals mx plus b is the equation of a straight line, in y equals ax squared plus bx plus c is the equation of a parabola that most of you learned from high school. And when we have an equation y equals b0 plus b1x, the b0 of course corresponds to the b1 corresponds to the slope, and we can estimate it. But in this particular case, we have the x and the y, that's numbers 1 and 2 and 7 and 14.3 and 3 and 12 point, let's make it 4. These are bad choice of numbers because I'd like to have numbers that when you graph them, you don't get a straight line. You get something like this. This is the x and this is the y, and the graph goes something like this. Now, again, these are not numbers that I just wasn't able to prepare that. Or for example, the numbers look something like this, even a full parabola. So, or part of it. So how do you deal with that? So the answer is by recognizing that if you create another column, using chapter 14, the ability to create another column, call it x squared. But x squared is simply like, x1 squared. Let's call that x2. So now we have an x1, we have an x2, which happens to just be x1 squared. So now if x1, so this will be a 1 in this case. This will be a 49 in this case. This will be a 3 squared or a 9 in this case. You simply square it. And now you throw into the computer 3 columns of data, including the y, the original x1, and this new column x1 squared. And when the computer prints out for you the multiple regression printout, b0 plus b1 x1 plus b2 times x2, well, the b0 is going to be the number that we're looking for, represents the c. The b1 part of the printout, the number in front of the x by itself is going to be the b of the original high school number in front of the x, and the number in front of the x2, which is the coefficient in front of the remember x2 is really x1 squared. That's going to be the impact of the quadratic. So for example, if you remember from high school that if you have a parabola like this, the a would be less than 0. I'm sorry, positive would be greater than 0. The number in front of the x is a positive number. The parabola opens upwards. If you have a situation like this, where that's what happens when you rush. If the picture looks something like this, or part of a picture like this, then the a would be less than 0. But after all is said and done, you're going to be typing in. You're given 2 columns of data. But when you notice there's a curve, you create the 3rd column on your own. You then throw this into the computer, and the computer will then print out the measurement. Will give you the a, the number by itself. I'm sorry, the c. It'll give you the b, and it'll give you the a. But so you can write out the equation. So you may get, for example, y hat equals 3 plus 2x plus 0.05 x squared. This might be a typical where again you'll see this is x2, but really to be interpreted as x squared. You can then plot the straight line, plug in, let's say x equals 1, and so if x equals 1, what happens? Well, x equals 1, you get a 1 here, you get a 1 squared over here, and the y is equal to, let's say, 1 plus 0.05 plus 2 plus 3, so it's 5.05. So if x equals 1, you're going to get 5.05. You get a point over here. And when you graph, basically the data, when you graph this should be basically correspond to the data coming up over there. Once we have this printout, we can then answer questions like we answered in chapter 14. Is the overall model useful by the F-test? Or we can test to see specifically, in other words, adding on this quadratic term. Let's go back to this picture over here. Brian, can you aim here for a second? Here, it's not clear. Is this a curve to the data or is it a straight line to the data? So the computer will tell us if adding on the extra x squared, in other words, is this second variable significant? By looking at the t-test, testing if beta 2 is equal to 0 will tell us if the quadratic is truly significant or not significant. If it's not, you just drop it out of the equation and deal with a simpler straight line equation, which would be the practical thing to do.